Okay. So since the time is 12:30, so we'll start this meeting. So today, what we will be discussing is about heap sort. So we have discussed about several algorithms of sorting before, such as quick sort, merge sort, and other non-recursive algorithms such as bubble sort, insertion sort, etc. So this heap sort basically is going to sort an input array by using the concept of binary trees. So before going for heap sort, so we'll first take a look at what is a heap actually. So before going for heap sort, we should know the data structure known as heap, right? So first, we should understand what is meant by a heap. So heap is nothing but a binary tree data structure. By this time, you might have studied about what is a binary tree data structure. So a binary tree will be converted into a heap if it has two basic features. So a binary tree is called a heap data structure if it has two features. So first is it should be a complete binary tree. So what is meant by a complete binary tree is nothing but, so it has its leaf elements towards left. That means left side of the tree has more number of leaf elements. So you might know what is a leaf and what is a parent node by this time. So leaf does not have any child nodes, whereas a parent node should necessarily have at least one child node. The maximum number of children for a parent node is 2 for a binary tree. And the right side may be, right side of a particular binary tree may be full or not full. Or that means it may be partially full, but the more number of children are there in left side. That means when a child node is inserted to a parent node, first the left child will be inserted. That is, such a tree is known as a complete binary tree. That means when a new node is inserted into a given node where it has vacant number of child nodes, so then if it has no any child nodes, the first child will be left and the second child will be right. So such a tree is known as a complete binary tree. So that is the first requirement for a data structure to be called as tree. So it is not enough to be a heap, but it should have the second property, which is any parent, any parent node should have a value greater than its child nodes if it is a max heap. So there are two kinds of heaps known as max heap and min heap. So if it is a max heap, if it is a max heap, so the parent node should have a value. That means the value in the parent node should be higher than the values in each of its child nodes. So this property should be true for each and every parent node. For each and every parent node of the binary tree, the value stored in the parent must be greater than the value stored in each of its children. So in that case, it is called a max heap, otherwise it is a min heap. So in the algorithm that I explain you today, I will be using max heap. So our intention is to sort a given input numbers, a given array of input numbers in ascending order. So in order to arrange or sort numbers in ascending order, we should have to use this max heap. So what are the two requirements of being a heap data structure? That means it should be a complete binary tree and it should be arranged as a max heap or a min heap, one of them. We will be considering only max heap. So it should be a binary tree and it should be arranged as a max heap or min heap. Right. So that is how a heap is built. That is the data structure known as heap. Okay. Now you got an understanding about what is a heap. And so we'll remind some of the key features of binary trees in order to understand this heap sort algorithm. Right? Right. So the first thing is, so if you consider the index of a given node as I. So the index is not the value stored in it. You must have understood by this now. So the index is index is used to find the location of a node in a binary tree, just like a linear array, just like a one-dimensional linear array. The array index is used to find the location of the particular array element. So likewise, in the binary tree also, the index I is used to find the location of the particular node. So according to the way this binary data structure is created, it is always for a complete binary tree having this children lean towards left. So always the left child will be given by 2 times I plus 1 and the right child will be given by 2i minus 1. So if the parent's index is I, the left child's index will be given by 2i plus 1 and the right child will be given by 2i minus 1. So this is for refreshing your knowledge on binary trees before going into heap sort algorithm. So in the other way also, so this is finding a child if the index of the parent node is known. So how to find the index of the parent if the index of the child is known? So that next is the that will be the next key point, right? So if the index of the parent or if the index of the parent of a child node with index I is given by flow I minus 1 divided by 2. Flow means round down. I minus 1 divided by 2. So if the child node's index is I, its parent index is given by this function I minus 1 divided by 2 flow. So that you should have to keep in mind. So we'll demonstrate this using a simple example in a little moment, right? Okay. So the other key point that you should know is that so in a complete binary tree, all the nodes are not parents. All the nodes are not parents. There are parent nodes and along with that there are child nodes. There are parent nodes and child nodes, specifically parent nodes and leaf nodes. So leaf nodes are the nodes which do not have any children, leaf nodes. So in heap sort, what we are interested is not the leaf nodes, but all parent nodes. What we are interested is the parent nodes. So in a given binary tree, the first parent will be given by the index n over 2 minus 1. That is, we have to round down or get the flow function, where n is the size of the binary tree. So these three facts I'll demonstrate using an example. So this binary tree I have created. So this has 5 elements, 1, 2, 3, 4, 5. So n is equal to 5. And at the top I have indicated the index of each of elements of this binary tree: 0, 1, 2, 3, 4. So this is a complete binary tree. Why? Because if you divide this binary tree into 2, you can see that it is elements are lean towards left. Elements are lean towards left, and it is not necessarily a full binary tree. Need not to be a full binary tree. So it is a complete binary tree. And we'll check each of them one by one. So if the parent node is I, so for example, consider 1. If the parent node is 1, so the left and right should be given by these two equations. So if I get 2y plus 1 here, 2 into 1 is 2, 2 plus 1 is 3. So okay, the index of the left child has been given by 2y plus 1. So 2y plus 2 is nothing but 4. That is the, sorry, this should be 2i plus 2. I have made a mistake here. 2i plus 2, not 2i minus 1. So the right child should be given by 2i plus 2. That is, if we get the I as 1, I equal 1, 1 into 2 is 2. Sorry, this is 2i plus 2. Again, I made this. This is 2i plus 1 and this is 2i plus 2. Right? So this is 2 into 1, 2. 2 plus 2 is 4. Okay. So the index of the parent with the child node I is given by I minus 1 divided by 2. So for example, we'll take this element. So this is a child and its parent is this node. Its parent is this node. We will check whether the index of the parent is given by this formula, I minus 1 divided by 2. So I is 4. 4 minus 1 divided by 2 is 3 divided by 2, 1.5. 1.5 flow function is 1. So okay, the parent is given by 1. And also we will check for this one, 2. 2 minus 1 is 1. 1 divided by 2 is 0.5. Flow value of 0.5 is 0. Okay. So that is also fine. So the first one and second one is true. And the third point, for a complete binary tree, index of the first parent is given by n by 2 minus 1. So what is n here? N is 1, 2, 3, 4, 5. 5 divided by 2 is 2.5. 2.5 minus 1 is 1.5. 1.5 flow function is 1. So according to this one, the first parent index is 1. Is it true? So this is a leaf node, this is a leaf node, this is a leaf node. And okay, this is the first parent and its index is 1. So this is the first parent, this is the second parent. So the parents will be counted from trees down to top. When we are moving from trees down to top, this is the first parent that we meet and this is the second parent that we meet. So if we want to find the parents of tree, the first parent is given by n by 2 minus 1. The second parent n by 2 minus 2. So n by 2 minus 1 is 1, n by 2 minus 2 is this one. And the last parent that we meet will have the index 0. The parent with index 0 is known as the root of the binary tree, and there are no parents with index less than 0. That means no negative index parents are there in a binary tree. So the root will have the index 0. So you should have this basic knowledge before you are going to understand the heap sort algorithm. Right. So how to convert a given, so this is a complete binary tree. How to convert this into a heap? So in order to be a heap, it should be a complete binary tree, and it should have either max heap or min heap. That means in max heap, the parents are less than the child. Sorry, the parent is greater than its children in max heap. So we need to have a function to convert a given binary tree into a heap. So that is known as heapify. Heapify. That means converting a binary tree into a heap. So that should be your first function or the algorithm that you should understand in this heap sort. Right. So we can modify a given binary tree to a max heap by using a function known as heapify. Right. And the fact is that heapify is called for all non-leaf elements, or in other terms, parent nodes of the binary tree starting from the first parent. So how to do that? This is how we are going to do that. So if you understand about the binary tree, so you must be able to understand that. Since we are calling heapify function for all parents, so I told that the first parent is given by NO2 minus 1, then the second parent NO2 minus 2, the third parent NO2 minus 3 up to 0. 0 is the last parent, root node. So that's why I'm using this loop, for loop 4. For integer I equal NO2 minus 1. So this is the first parent up to the root node I greater than or equal to 0. We have to reduce the increment by 1 by 1. First we will use NO2 minus 1, then NO2 minus 2 like that. Then we are going to call this heapify function, and the implementation of heapify I'll describe this in a little moment. So what this heapify function will do is, it will take an array, or in other terms, so this array is represented in as a, so this is a binary tree. So this array is arranged as a, so this capital A is a complete binary tree, and this n is the size of the binary tree. N is the size of the binary tree, and I is the parent node, which we call heapify, because heapify function is called for all parent nodes of the binary tree starting from the first parent. So I will be NO2 minus 1 in the first instance, then it will be NO2 minus 2 up to I equals 0, up to root node. So heapify is called for all parent nodes. So what is heapify function? Now we will write a pseudocode to implement the heapify function. So as I told you, the first is a complete binary tree. So the first element or the first argument of this heapify function should be a complete binary tree. So a complete binary tree is nothing but a array. An array can be represented as a binary tree. So what is given as the first input? What is given as the first input is nothing but this is the complete binary tree. And this is, as I told you, it is the size of the binary tree, so which is an integer. And this is the index of the parent. Index of the parent node, again, that is also an integer. And this heapify function does not return anything. It will just rearrange the elements. So it is not having a return type. So I'll call it void. Void is for return type which does not return anything. Right. So we'll go for this implementation. So the heapify, first what it will check is whether this index I is less than NO2. Why? Because the first because this heapify is not useful for leaf elements. Heapify is intended only for parent nodes. Due to that, it will check. So as you can see, the first parent node is NO2 minus 1. So that means I should be less than NO2. So this heapify function should check whether I is less than NO2 to check whether this index I is actually a parent node. Otherwise, if it is greater than or equal to NO2, so that is a leaf node. So then there is no point of calling heapify for leaf nodes. So you will understand what is this heapify when you completely, when I give a complete brief of this function, and with an example, you will understand what is the purpose of this heapify function. Right. It will first check whether it is a parent node. Okay. If it is a parent node, we will make an integer known as largest. So I use this integer known as largest to store the index of the largest element. So in heapify, what we are going to consider is the parent node, the left child, and right child. We are going in heapify function, we are going to consider the parent node, that is the index with element I. Element I is the index of the parent node. So what we are going to consider is the left child and the right child value. So first we make the largest index, or I use this as largest index as I, that is the parent node. Parent node is made the index which has the largest value, but we have not checked whether it has the largest value or not by this time. Then, so as I told you in the previous slide, if the index of the parent is I, the left child will be given by 2i plus 1. 2i plus 1. So we make the index of the left child as 2i plus 1. That is obvious, that I explained in the last slide. And we make the index of the right child as 2i plus 2. Index of the right child is 2i plus 2. I explained in the last slide. Right. So then we make a comparison. The first thing that we are going to check is whether this left child index is less than n. Why we are doing this is because in a binary tree, what is the maximum index in a binary tree? The maximum index in a binary tree is n minus 1. The maximum possible index in a binary tree is n minus 1, where n is the size of the binary tree. Just like an array, when the array size is n, the highest index is n minus 1. So it is similar in binary tree. When the binary tree size is n, the highest index is n minus 1. So when we calculate the left child as 2i plus 1 and right child as 2i plus 2, if the left child is greater than n, then that child is not in the current binary tree. That means there is no point in doing that. So first we check this condition, whether the left child is less than n, because the highest possible one is n minus 1. If it is greater than n, we don't do this comparison. And not only that, that means the left child must be inside the tree. And if the value of the left child, so left is nothing but the index of the left child. This is the index. So using the index, we can find the value of the left child using capital A square bracket index. So this is the integer value of the left child. So if the value of the left child is greater than a largest, so what is largest? Largest is I. I is the index of root. I is index of root here. So if the left child is greater than the value of the root element or the parent, so this is parent here. If the value of the left child is greater than value of the parent, then that means the index which has the largest element should not be I, it should be left. The index which has the largest element should be left now. No, so we have initialized the index. So this largest, the value stored in largest should be the index which has the largest element. So we have made the index as the parent index in initialization, but we are going to check whether it is true or not. So we are going to check that with the left child's value. If the left child's value is greater than the parent's value, then that means the left child's index must be the largest index. The left child's index must be the largest index. That is the argument here. So if the left child is greater than the parent, then left child index should be the largest index. So left child index is 2i plus 1. So similarly, we can do that for the right child also. So first we are going to check whether right child is actually a member of the tree. So if the right child 2i plus 2 is actually less than n, that means it is a member of the tree. And the right child, so a right is the value of the right child is greater than a largest. So assume that in this step, largest value was set as left. So when it comes to this point, a largest will be not the value at the parent, but at this point, if largest was set as left here in this step, when it comes to this step, a largest will be the value at left. So if this is true, if the value at left is less than the value at right, then that means largest should be right. But if this was not true, that means largest is not left, but largest is I. That means still largest is the parent node. Then this will compare the right child against a largest. If this is not set, then it will be checked against the parent node. The right element will be checked against the parent node. if the right element is greater than the parent node, or if this was set greater than the left node, then largest will be right. So this is just the setting the index of the largest out of the parent node, left node, and the right child, left child and the right child. So by this moment, we have compared each of the parent, left child and right child, and decided what is the index of the largest element. And now we check whether largest is not equal to I or not. We check whether largest is equal to I or not. If the index, if if the largest index is equal to I, then there is no problem. Why? Because in a max heap, what we defined as max heap was the parent node's value should be greater than its child nodes. The parent node's value should be greater than its child nodes. If the largest node, if the value of the largest index is equal to I, then that means the parent node is the largest element. But in case if one of these if conditions is true, that means if the left child or the right child or both or one of those things is the highest uh, element, not the parent node, then largest will be either left or right. Then this will be true. Then largest will not be I. So I is what? I is parent node. So if one of these if conditions is true, that means if left child or right child is greater than the parent node, then we should do following. Then we should swap. AI. I means what? Parent node. We should swap the parent node's value with the largest value. So the largest will be either left or right. Because largest is not equal to I, largest will be either left or child. So for example, assume the largest is left, largest index is left. So in that case, if the largest element is not the parent node, we should swap the parent node's value with the left or right, whichever the largest element, we should swap with the parent to make, why we swap? We swap to make this a max heap. So if, for example, if the left child is the largest, if we swap the left child with the parent node, then it will become a max heap by making the parent node largest. So this swap operation will make the parent node larger. So there is no requirement of this swap operation if largest is equal to I. If largest is equal to I, we need not to swap. But if largest is not equal to I, that is either left child or right child is greater than the parent, then we should swap. But not only that, this heapify function is recursive. So when we swap the parent with the child, then we should check whether that child is again whether we should check whether that child is heapified or not. So we have to recursively call this heapify an. So we have to recursively call it for this index. So for example, if we are coming here, if either largest is left or right. For example, let largest equal left. So we should first swap that left element value with the parent node And after swapping, we should heapify that left, or if largest is left, we should do the heapify for that swapped element. That means this left or right. If largest is left, we should do the heapify for this binary tree, the same binary tree for the left element. So this is the how this heapify function is work. So you may not understand what is the purpose of this heapify function by this format. You will understand it through an example definitely. So in the same time, we will consider what is the complexity of this heapify function also, because we have to analyze the complexity of heap sort in the coming slides. So what is the so this is what this is heapifying the whole binary tree. This is heapifying the whole binary tree. This is not part of a heapifying function. This heapifying whole binary tree is part of the heap sort algorithm. So I mentioned this here because we need to call this heapify function starting from the first parent up to the last parent. So that is part of the heap sort algorithm. I just mentioned here to give you an understanding why we are using this heapify function only. So when we get the implementation of the heapify function, when we get the implementation of this heapify function, so it should be like this, and each of this heapify called in this heapifying this binary will be like this. It will be like this. This is the implementation. So in this case, we have order 8. Why? Maximum. I'm using the maximum. Maximum here will be 1. If this is true, 1, 1, 1, 1, 4, 5, 6, 7, 8. 8. So this has 8 operations. 8 operations. And what about this one? This is variable. This is variable. If this is true, if one of these true, then this will be executed. Otherwise, it will not. And also, there is a recursive heapify function. That means this heapify is called inside the same function. So we discuss what is recursive function in both merge sort and pick sort. In heap sort also, this recursion is used. So this one's complexity is different based on whether this largest is left, right, or I. If largest is I, then only this will be theta 1. Only this will be executed. None of these will be executed. So it will have the best case complexity of theta 1, and worst case it will be this one. It will be the order of, so I'll consider this one as complexity as h dash n. I'll consider this one as h dash n. So we have to heapify the subtree. So if this is true, we have to heapify the subtree starting from the left or right side. So we'll consider what will be the worst case complexity. So by combining these two, we can, so I use Hn as the complexity of heapify function, not the heap sort, not heap sort. We have still not come to heap sort. We are still in heapify function. So what is the purpose of heapify function? Heapify function is used to convert a given binary tree into a max heap. Converting a given binary tree into max heap, or in other words, heap data structure. Converting a binary tree into heap data structure, we use heapify function. Right. So by adding these two, so we can write the complexity of this Heap function as hn plus theta 8 plus h dash n. Right. So we will consider what is the complexity of h dash n in worst case and best case. So for the best case, I told you that it is very easily understandable. The best case is largest equal I. Best case is largest equal I, then none of this will be executed. So it is having theta 1. And the worst case is when this is true, and this is true, this is 1, and then this swap operation will take place. Then this swap operation will take place, and this heapify will take place. And this heapify is having log 2 n by 2. Why it is having log 2 n by 2? Because I'll tell it by using the previous binary tree, this one. So assume that we call heapify for this node. Assume that we call heapify for this node, and uh, we will come to this left child. That means the largest is equal to left child. Largest is equal to left child. Then what will be the maximum complexity? So what we'll do, heapify do is it will swap. If the left child or right child is greater than the parent, it will swap. So in this one, assume, so here the left child is not greater than the parent, but assume assume that the left child is greater than the parent, and this was swapped. So then it will come here, and heapify will be called for this node, because left the largest was not I. So heapify will be called for this one. Then it will check between these left and right, and again if this was if this is highest, so actually this is highest, 7 is greater than 1, so again this will be swapped, 7 will come here and 1 will go here, then heapify will be called for this one, and this will be continued like this one. So you can see for a given level, so there are 3 levels, 1 2 3. There are 3 levels in the binary tree. For a given level, this heapify function will be called only one time. For a given level, heapify function will be called only one time. So the number of levels in a binary tree will be given by log 2 n plus 1. Log 2 n plus 1. So the complexity, so the complexity of, so if this is the parent node, and the complexity, so this is, so this, if this is hn, so I'm describing the complexity of heapify function. If this is hn, right, if this is hn, complexity of this heapify function is, I represent as capital Hn. The complexity of this function will be n by 2, because there are only n over 2 parent elements, and heapify will be called only for parent elements. Heapify will be called only for parent elements. So the number of the number of levels, of parent elements. So the number of levels of parent elements is nothing but n over 2, because heapify is called only for parent elements. The number of levels of parent elements can be given by log n over 2, log 2 n over 2 plus 1, and the plus 1 can be neglected when we get the order. When n is very high, when simple n is very high, so in asymptotic analysis, when we get this theta or the order log 2 n over 2 plus 1, plus 1 can be neglected. So it is in the order of log 2 n over 2 because we are only using heapify function for n over 2. For n over 2, but there are only n over 2 parent levels. So it will be n over 2 log 2 n over 2 plus 1. Plus 1 we can omit because of asymptotic analysis. When plus 1 is compared with log 2 n over 2, plus 1 is very less significant. So plus 1 can be omitted. So it is having the complexity in order log 2 n over 2. So Hn is, so we can write the base case by combining this. So in base case, it will be theta 8 plus h dash n theta 1, it will be theta 9. And in worst case, it will be theta 8 plus theta 8, so this should be plus. This should be theta 8 plus theta log 2 n over 2. It will be theta 8 plus log 2 theta 8 n over 2 again. So this theta 8 does not have any significance when it compared with this one. Again, it will be in the order of log 2 n by 2 in asymptotic analysis. So the heapify function is having worst case complexity of log 2 n by 2 and best case complexity. That means if the parent node is already the highest, then it will have only 9 operations, only 9 instructions. Otherwise, it will go and go. It will cause this heapify function to be called again and again. It will be called again and again to make this operational, right? Okay. So now, before going for heap sort, so as you must have an understanding about what is going on with this heapifying function. What is happening with this heapifying function? So if you didn't understand this algorithm, don't worry much because you can understand. For those who didn't understand this algorithm in this manner using this pseudocode, you may be able to grasp this one using this example. So I will take this binary tree as the example. This binary tree. So this is the complete binary tree. I'll take this one as the example and I will call heapify function. How to make this binary tree a maxi? That is by calling heapify function starting from the first node. First node is 1. So we call heapify function for this node. Then after finishing that one, we call heapify function for the second parent. For the first parent, we call heapify function. Then for the second parent, we call heapify function. So that is by doing this for integer I equal n over 2 minus 1. That is the first parent to the last parent, we call heapify function. So in this example, it will be what I am going to demonstrate in this example is nothing but that one. Starting from the first parent to the last parent, I am going to call heapify function for this binary tree. So this is the same binary tree that I showed you before. This is the binary tree that I showed you before. So now I'm going to heapify function for this one. So the first element, so this is n is, so here n is 5. So the first parent node will be given by n over 2 minus 1. N over 2 minus 1 is 2.5 minus 1. is 1.5. 1.5 flow value is, or the round down value is 1. So the first parent is given by 1. I already explained you this one before. How to get the first parent, I already explained you. So the first parent is 1. So that means I is 1. So what will be the first function called? Heapify A5 1. So Heapify A5 1 is called. What will this Heapify A51 call? When this is called, what it will be done? What will be done is nothing but this. What will be done is nothing but this. Heapify A51 is called. So first it will check whether this is true. N divided by 2. 5 divided by 2 is 2.5. When this is float, that will be 2. The value of I is 1. So 1 is less than 2. So that means all of these instructions will be executed. That means this checks whether it is a parent node. So it is a parent node. I equal 1 is a parent node. So when Heapify A 1 is called, it will first check whether it is a parent. Yes, it's a parent. So then next what? The largest will be set as I. Largest will be set as I. So here I is equal to 1. Largest is set as 1. That means largest will be set as 1, this index. And next, the left child will be 2i plus 1, right child will be 2i plus 2. What will be the left child? Left child will be 2i plus 1. 2 into 1 is 1, 2. 2 plus 1 is 3. 3. And the right child is 2i plus 2. So the right is 4. And it will now check whether this condition, left is less than n, and the value in the left element is greater than the value in the largest element. Okay, we'll check whether this is true. Left is 2i plus 1 is 3. 3 is less than 5. Okay, so this leaf node is an actual leaf node inside the binary tree. So then there is no problem. This condition is satisfied. Okay, left is less than n. The value in the left side element is greater than value in the largest. Largest is now here I. Value in the left. Value in the left. So what is the value in the left? 6. So A left is greater than AI. I is 1 here. A largest is 1 here. A largest. So A left is greater than A largest. So this is true. A left is greater than A largest. That is, value in the left child is greater than value in the right child. So that means largest should be set as left child. So since value in the left child, so when I is equal to 1, when I is equal to 1, this will be the parent node, and this is left node, this is right node. So value in the left child is greater than value of this parent node, so that largest will be set as this index 3. Largest will be set as left. Left is this index. And again, now this is step. Whether it will check whether right is less than n. Okay, right is what? 2i plus 2, it will 4. 4 is less than 5. Okay, this is true. And the value in the right element greater than A largest. So now the largest is 3. So A4, it will check whether A4 is greater than A3. So we'll check. Now it will check whether A4 is 7. A4 and A3 is 6. That means value at third index. A6 is 6. A4 is greater than 6. That means 7 is greater than 6. So A4 is greater than A3. Then this index, right, should be largest. So we set as that if condition was true, we set largest as 4. So now what happened? So now largest is 4. So that largest is not equal to I. I is 1 here. So largest is not equal to I. So then that means inside this we should do. So we should swap as largest is not equal to I. We should swap AI with A largest. So we should swap. So what is AI? AI is 1. What is A largest? A largest, so largest index is 4. A largest is 7. So we should swap 7 and 1. We should swap A1 with A4. So A1 is what? This is I. We should swap AI with A largest. So A largest is 4. A largest is 4. AI is 1. So we should swap AI with A largest. So then what we will be getting is this tree. What we will be getting is, so we swapped 7 with 1. We swapped 7 with 1. Okay. Then what will happen according to this algorithm? According to this algorithm, swap AI with A largest. Okay, we did. Then heapify A n largest. So what will be A n largest here? So heapify A n is 5, largest is 4. A n largest. But what will happen is this. So this I will be 4. So when it comes to here, I is now 4. 4 is not less than 5 over 2. This will be 2, 5 over 2. So 4 is not less than 5 over 2. So this will not be executed. That means only one. So only when it comes to this if condition, it will terminate that heapify. So that I have written here, heapify A5 with 4 will not make any change. Even though, I mean, so this, so even with this figure you must understand. So what is this? This is a leaf node. Heapifying is not done. It will not make any change for leaf node. Heapifying will not alter any leaf node. Calling heapifying for leaf node will not make any change. That is the thing that you should understand. Right. So next thing. Now this heapifying. So one iteration of this loop is now over. Heapify A51 is now over. So then I should be decremented by 1. So now I will be, so here I was 1, then now I will be 0. So now I is 0, heapify A50 is called for this tree. For the new tree, where we swapped 7 and 1 here. For the new tree, A50 is called. So when A50 is called, so 0 is less than 5 by 2, obvious. So largest will be first set to 0. Then it will check. So now I will not go to the previous slide and explain. Now you should have some understanding how this algorithm heapifying function works. So it will check against the left child. So what happens? Left child is 7 and the parent is 2. So left child is greater than 2. So what will it do is, the left child index is 1. So the left child index will be set as the largest index. Largest index will be now 1. Then it will come and check the right side. Then it will come and check the right side. A right is 3. And here, now the largest index is 1. So it will check. So I'm describing about this step. I'm describing about this step. This is however true. This is true. So A right, it will check whether A right is greater than A largest. So what is A right here? Here A right is 3. A largest, so largest is now 1. A largest is A1. A1 is 7. So A right or A2 is not less than, is not greater than A largest or A1 is 7. So that largest is still 1. So because of this, simply the right element is not greater than the largest element in the current moment. So this is the largest element in the current moment. So the right side element is not greater than this one. So largest is still with this index. And it will now check whether largest is greater than, sorry, not equal to the original index or not. Original index means I. So largest is 1, it is not equal to 0. So it is not equal to 0. So then we should swap this one. We should swap. So swap A1 with A0. Swap A1 with A0. So when we do that, what will happen is, it will come like this. 2 and 7 are 7. So now again, so the heapifying function should be called for this index largest as, so this is not equal to I. So next thing is calling heapify again for this index. Heapify A 5 1. So heapify A 5 1. So because as this is not as this was not the largest element, as this was not largest element, we exchange. So after exchanging, we should check whether the resulting tree is a max heap or not. That's why we do this again. So after the swap operation, this tree may not longer be a max heap. So we should ensure by calling on the index which was the largest and check whether this is already a max heap or not. So what we did, we swapped this one. Then for this index, we call heapify. So first we should check whether this is a parent node. So n over 2, 5 over 2 is 2 and 1 is less than 2. So this is a parent node. So heapify function should continue. Okay. Again, the same heapify function will take place. So here I is equal to 1. Here I is equal to 1, so that largest is set as 1. And it will check. Okay, first this will be compared. 6 is greater than 2. So this index 3 will be set as the largest. 3 will be set as largest. Then this element A largest will be checked against A right. This is A right, but A right is less than A largest. That means 1 is less than, because 1 is less than 6. A right is less than A largest. So still largest is 3. Largest is 3. So now largest is not equal to the original index. Original index is 1. 1 is not equal to 3. So we should swap. We should swap. Swap A1 with A3. When we swap, we get this tree. When we swap, we get this tree. 2 will come here, 6 will go here. Swap, and now we have to call again heapify A5 3. But A5 3 no change, because this is a leaf node. You can understand when you go to that algorithm. So what is this? So by calling heapify on starting from the first parent node uh, to the last parent node, we have been able to convert this uh, binary tree or this complete binary tree into a max heap tree, or in other terms, max heap data structure or max heap tree. So is this a max heap tree? So what is the requirement of a max heap? All the parents must have values greater than each child nodes. We'll check for this parent. 6 is greater than both 2 and 1. Okay, this parent is okay. 7, this parent. 7 is greater than both 6 and 3. Yes, this is a max heap. So I told you this heapify function is called from first parent to the last parent to convert a given binary tree into a max heap tree. So this is the first step of heap sort. So for any size, so this is n equal 5. So when you call this, when this only this small code, so the code is only this much small, but there is lot of things that you should understand, both recursion and swapping and indexes. You should have a lot of internal understanding with you to understand this heap sort algorithm. So whatever the size of the tree, by calling this heapify function, starting from the first parent to the last parent, you can convert a given binary tree into a max heap. That is the first step of heap sort. Okay, so I hope you are very clear with how to convert a given binary tree into a max heap, both in pseudocode and using this example. I think you must have cleared your doubts on heapifying function. So that is the first step of heap sort. So now you have got the basics or the prerequisites to understand the heap sort algorithm. So now we will go for the heap sort algorithm, right? So up to this point, I only described what is heapifying and what is a max heap, how to convert a given binary tree into a max heap. So now we'll come to the real implementation of heap sort. So heap sort does not have return type. It is a sorting algorithm. That means rearranging of the elements. So it has a given input in terms of a binary tree. So you can consider it as an array or binary tree. So array is a linear array is equivalent to a binary tree. So you can represent it as a binary tree or an array. So this could be an array or a binary tree, right? And this is the size. So the arguments for the heap sort is nothing but the input array or binary tree and the size of that array. And the first thing we have already done. So this is what we were discussing throughout this whole lecture. From starting from the first parent to the last parent, we should heapify. Why we are doing this? To convert the original binary tree to a max heap. We already did that. I already explained that. So after that, what happens? So how to heap sort? So after that one, what we will be doing is we consider from last element to the first element of the max heap. So we consider from last element to the first element of this max heap. So after doing this, so this for loop is not inside this for loop. This for loop ends here. This for loop ends here. That means after heapifying the binary tree, this for loop ends here. This is over. Now there is a max heap like this one. So now we are So what is input for the heap sort is this one. After heapifying, what we are remained is this one. So what is input is this one. This is the binary tree. After heapifying, it will become a max heap. So for this loop, for this for loop, what will be input is not this binary tree, but this heapified or the max heap, heapified binary tree, or in other words, so what is input for this for loop is this heapified binary tree or max heap, not this one. So by you running this for loop, we convert the binary tree into a max heap, then input that into this for loop. In this for loop, what we are doing is we will be considering from the last element to the actually the second element. So I equals 0 we are not considering. I equals 0 we are not considering up to from n minus 1, that is the last element, to the second element. That means I equal 1. In this loop we will be doing this one. What we will be doing is swap A0 with AI. What is swap A0 with AI? A0 means 0 is the root. 0 is the root. I is this one, this index, n minus 1 up to A1. N minus 1 up to A1. Extend root element with last element. Why I call this one last element is at the end of each iteration of this for loop, the last element will be removed. The last element will be removed from the binary tree. The last element from the binary tree will be removed. That's why I call this exchange root element with the last element. So you will understand this one. At this moment you may not be able to grasp this one, but with example you will understand this one, right? So we exchange the first element with this ith element. I will be given by this one. I will be given according to the loop value. So we exchange first element. So the root element is, so since this is a max heap, A0 has the highest value in a max heap, or the root node. So if you saw this one, so what is stored in the max heap root node is 7. 7 is the highest value of this tree. So in a max heap, root node has the highest value. So what we are doing is we exchange root node with the last node. This is the last node. This is the last node. We exchange this one with this one. We exchange this one with this one and heapify starting again. So why we are doing heapify? Because, for example, we exchange this one with this one, then what will happen? 7 will come here and 1 will go here. So we will be heapifying starting from this one. So the 7 will come here and 1 will go here. Then if you consider the remaining tree, it is not a max heap anymore, because 1 is here. One will go here, then it will not be longer a max heap. So that we'll have to make this one a max heap again. But we disregard the last element. How we disregard the last element is we call I 0. I is what? I is the size of the tree. I is the size of the tree. When, for example, when I is equal to n minus 1, the size of the tree will be n minus 1. Then automatically, when size of the tree is n minus 1, automatically the last element will not be considered. That means when we swap 7 here, when 7 comes here, and we call heapify AI0, this element will not be considered because the size of the tree will be now n minus 1. So the last element will be removed in heapify. And we call heapifying for this element, the root node, AI. So this is the node which we call the heapify. So we call heapifying for the root node. So when we swap, this will not be longer a max heap. So what we are going to do is we will convert this into again a max heap by calling heapifying on the root. But since we use the size of this heapifying function as I, which will be reducing by 1 in each of the iteration of this for loop. In each of the iteration of this for loop, I will be decremented by 1. So the size of this heapifying function also decremented by 1. That means the last element will be removed and it will not be considered. Why we are removing the last element is when we swap. So when we do this swap operation, it is we are doing for a max heap. We do this swap operation for a max heap. Why? In the first step, when I is equal to n minus 1, we have the max heap resulting from this one, this outer for loop. We have the max heap resulting from this outer for loop. Then when we come here for the first time, we are doing swap for a max heap. And when we exchange the root with the last element will be the highest element. Last element will be the highest element. Right. So the last element will be the highest element is, so we have the last element of the ascending order. That means the last element which comes after the swap operation is sorted. That means that element is already in ascending order because we take the root element of a max heap. Root element of a max heap has the highest value. We get that as the last element. We exchange that as the last element. Then this will be automatically sorted. Then we convert the resulting tree excluding the last element because this I is decremented by 1. So the last element is not included. We call the heapify for the root. When you call heapify for the root, then it will be converted again back to a max heap. So when I is reduced by 1, for example, when I is equal to n minus 2, in the next iteration, when we do swap, again we are doing for a max heap. Again we are doing for a max heap because this heapifying function converts the tree resulting from the swap operation again into a max heap. This will convert again into a max heap, and we swap that root with the last element, and the last element is removed, and we keep on doing this until all elements are sorted. So the last element that we get by swapping with the root of a max heap, we get the corresponding highest element of the tree. So we do this again and again until we get the correct ascending order. So that is how this heap sort works. So this is the algorithm. You will understand how this works using an example. So we already did this one. I explained using both the implementation of the heapify function and using an example how to convert a given binary tree into a max heap. So in this one, what will be done? We will discuss using an example. I'll demonstrate using an example. Okay. Now we will come to the complexity of this heap sort algorithm. So in this one, this is only executed one time. and I will be varying from n over 2 minus 1 up to I equal 0. So n over 2 minus 1 up to I equal 0. So 0 to n over 2 minus 1 things are there, and at the time of violation of this loop, it will be, there will be additional one, and this will be n over 2, because it is run from 0 to n over 2 minus 1. There will be n over 2 times this will occur. And what about the heapify? So heapify, I explained it as hn, and this will run n over 2 times. So the complexity of heapifying is hn for a heapify function of size n, and it will run n over 2 times, because it transforms 0 to n over 2 minus 1, right? So that is the complexity here, and here also this will be 1, and so we have to sort this one until n minus 1 to 1, up to 1 to n minus 1. There are n minus 1 times it will be run, and at the time of violation it will be, there will be additional 1, so it will be n, and this will do for n minus 1 times. And swap. So if this is true, so that means this loop when this loop is running, this will be swapped n minus 1 times, because the top element of the max heap will be exchanged with last element n minus 1 times. And heapify will also be called n minus 1 times, but the fact is the size of the heapifying function keeps on reducing. The size of the heapifying function keeps on reducing. First it will be n minus 1, then n minus 2 until 1. So the complexity will be addition of these one, hn minus 1 plus hn minus 2, because the size of this one keeps on reducing. First it will be n minus 1, n minus 2 until h1, because we specified the complexity for a heapify function of size n as hn. Hn was the complexity of a heapify function of size n. So for size I, it should be hi. So hi will be running from n minus 1 up to 1. So that will be the so this heapify function's complexity will be addition of this one, hn minus 1 up to h1. So the whole complexity of heap sort can be written as a summation of all these elements. So I represent the running time complexity of this one as this one. So actually I always forget, there should be so c times. So make sure that at least in your mind, so this number of instructions must be multiplied by a constant term into c to get the running time of this algorithm, because this is the number of instructions, it should be multiplied by a constant c. So how did I get in this n plus 2? N plus 2 I got by adding this. N over 2 plus n over 2 is 1, and this one 2. N plus 2 plus n over 2 times h, this one. Let me see if we find the original binary tree, and this one I will get 2n minus 1 plus 1 is 0, so it will be 2n. So n plus 2, 2n, n over 2 times hn, and this one n minus 1 plus these things hn minus 1 up to HR. So this is the complexity of, this is a general complexity equation for heap sort. Now we can reduce this one. So n plus 2, 2n, n minus 1. The addition of them has theta n in asymptotic analysis. This will come up to something like 3n plus something. So it is having theta n complexity, and we should investigate what is the complexity of this one, this CP5 and this CP5. So this CP5 and this CP5 are the things which will determine the complexity of this algorithm, this CP5 and this CP5. And the fact is, the running time of this CP5 is not the running time of this CP5. These CP5 functions are different to each other and will depend on different factors. And we will discuss what are those factors. Okay, so this is the generic equation, and now we will consider the worst case and best case scenario. Okay, so we deduce this equation for the heap sort algorithms complexity. Right, so we will consider the worst case and best case. So worst case is the input is in descending order. So when the input is in descending order, so the original tree is a max heap. Why I am calling that one? So assume that the first element of the array. So that when the input is in descending order, the first element, that means A0, will have the highest, A1 will be the next highest one, and A2 will be the next highest one. So when you insert each of these array elements into the binary tree, when you insert each of these array elements of a descending order array into a binary tree, it will automatically be a max heap. So when the input is in descending order, the resulting binary tree will be already a max heap, such that the n over 2 hn, which resulted this complexity, is this one, heapifying. Heapifying is the one which results n over 2 hn. So when the input is in descending order, this is already a max heap, so that this heapifying function will have the least, this heapifying function will have the least complexity. This heapifying function will have the least complexity, right? So heapifying this original tree, I mean this function, the complexity of this function will have least complexity, because in descending order the tree is already in max heap. But however, so after this one, even though this is in max heap or not, even though this input array is in max heap or not, after heapifying, when it comes to this for loop, it will be, there will be no change. This for loop does not know whether this heapified or the max heap tree was originally a binary tree, a normal unordered binary tree, was, or it was already a max heap, or it was not a max heap, does not matter for this one. This one's complexity will not change. This one's complexity will not change. And heapifying the root node, will have the highest complexity. Heapifying the root node, so since this one is 0, so root node is in the top of the binary tree. Heapifying the root node will have the highest complexity. So we will consider it as log 2 this size divided by 2. Log 2 this size divided by 2. So this one's complexity. So Tn. I mean, so when the input is in descending order, it is actually the best case. Sorry. So in when the input is in descending order, unlike in other sorting algorithms, most of the time when the input is in descending order, you get the worst case. But in heap sort, when the input is in descending order, you get the best case because the heap is already sorted. Heap is already in max heap. So there is no complexity. That means this heapifying. This is the heapifying complexity. Heapifying complexity will take the minimum time, right? So this is not the worst case. I have written it in the other way. So this is best case actually. Why? Because this is in descending order. This will take least time. Okay. Okay. So this theta n, there is no change. N over 2 Hn. So for the heapifying function, I told you that the best case running time is theta 9 and the worst case is log 2 n over 2. So this is the best case. So n over 2 times theta 9. And what about this one? And each of these are involved in heapifying the root. Heapifying the root is a case where it is a worst case for a given heapify. Heapifying the root, because the root is at the top, it may go all the way down until n over 2 levels. Until n over log 2 n over 2 levels, it will go down. It can go down. So it is having the higher running time. So we can consider it as log 2. So this size hn minus 1 size is n minus 1, log 2 n minus 1 over 2. This one log 2 n minus 2 over 2, likewise until log 2 1 over 2. And this is logarithmic addition. You can write as multiplication. So and also theta 9 is having the complexity in asymptotic analysis theta 1. Theta 9 is having theta 1 complexity, and this overall complexity of this term will become theta n over 2, and log 2, this is log addition, you can write as multiplication. N minus 1, n minus 2 until 1, and this one as multiplication. Then you can get the power. So this is in, so this is like so this and also we can combine these two, theta n over 2 plus theta n. It is again having theta n complexity, and this one log 2 n minus 1, this can be written as 2 to the power. So there are n minus 1 terms here. So it can be written as n minus 1 to the power n minus 1 over 2. And actually this should be in theta. This is in the order, not this is not equal to this one. This is in order. This is actually in order of this one. This is in order of this one, n minus 1. So if you get this one, it is like n minus 1 to the power n minus 1. This is in the order of that term. It is, even though this is not equal, but it is in order in asymptotic analysis. Right? The product can be written like this. is in this order, and you can get the index of the log out. N minus 1 you can take out of the log term, so it will be n minus times log 2 n minus 1 over 2. And when you take the order, it will become n times log 2n. When you take the order, so taking this order, you should have some understanding. So we talk when n is very large. We talk when n is very large. That means n approaches infinity. When n approaches infinity, n minus 1 over 2 can be written as n. When n approaches infinity, n minus 1 n. So this will be the addition, and theta n plus this log n times log 2n. N times log 2n has higher significance than n. So the overall order will become n times log 2n in best case. In here heap sort best case is descending order. Input is in descending order. So similarly we can discuss for the worst case. So this should be worst case. Okay, now okay. So the worst case is input is in ascending mode. That means the array is, you get input as an array already sorted. But the fact is, when it is put into the binary tree, it will be there as a min heap. So when an ascending ordered array is represented as a binary tree, it will be a min heap. So the first heapifying or converting the binary tree into a max heap will have the highest complexity. That means this term will now have the heapifying. The original binary tree will have the highest complexity. So input is in ascending order. Heapifying this one will have the highest complexity, but still heapifying the root node after converting this one into a max heap will take the same amount of time as it was in the base case. So this term, heapifying these root nodes, will take the same amount of time. So this n over 2 times hn. So now we can write hn as log 2 n over 2, because hn's worst case running time is now here, because this is in ascending order min heap. So in order to convert a min heap into max heap, it will have the worst case complexity. So it will be log 2 n over 2. So now what we will have to do is, we can simplify just like before. Log 2, this one can be simplified like this one, and this one as this one. And again we have to get this one in theta. This is in order that term. Okay, so this is again in like in the previous example, we can write like this one, and we can bring this one here out of the logarithm, because this is power. And now we can, since this is both log 2, we can add this one. So n minus 1 plus n over 2 is in the order of 1.5 or 3 over 2n, 1.5n, right? 1.5n, and n over 2 is, so this n minus 1 over 2 and n over 2 both are in the order of n over 2. Can be written like this, and this order in asymptotic analysis, 1.5 can be omitted and 2 can be omitted. Again it will become theta n times log 2n, and when this is added, the resulting one again will be n times log 2n. So again an important result will come here. So both in the worst case and the best case, that means regardless of whether the input is in ascending order or in descending order, it does not matter. What will happen is it will have the same complexity, because why? In the ascending order or descending order, only the heapifying of the original input will be the variable, and this sets after converting into a max heapifying, this will take a constant time. This will take a constant time, because of that, the heap sort's complexity is said to be irrespective of the input, whether the input is a descending order array or an ascending order array or an averagely sorted array. Whatever the input, the complexity of sorting is n times log 2n. Therefore, all worst case, best case, and average case complexity of heap sort is in the order of n times log 2n. So this is an important result regarding the complexity of heap sort, right? So that ends the complexity of heap sort. So what we are remaining to understand is, so I have already explained using an example how to heapify a given binary tree. Now we will see how the heap sort occurs after heapifying the original binary tree. So that one we will discuss. So after, so the first thing in heap sort. So the first part of heap sort is this for loop, which we discussed. If we find the original binary tree to form a max heap. Then the second part is removing, means that is the actual sorting algorithm. That means removing, that means exchanging the top of the max heap as the last element and removing the last element. That is this loop. So we exchange the top of the max heap as the last element and remove that last element and heapify the resulting tree. And we do this again and again to sort the tree. That thing now I'll do using an example. So we obtain this max heap tree by heapifying the original tree. This is the max heap tree that we get after heapifying the original tree that I explained already. So now I will explain this for loop in the heap sort algorithm. So now the first for loop is over. Heapifying the original tree is over. Now we will go from I equal n minus 1 up to I equal 1 and let you know how this heap sort occurs. So the first is I equal n minus 1. N is here 5. N minus 1 is 4. So here we have to swap A0 with A4. So in the max heap tree, A0 is 7, A4 is 1. So we have to swap. Swap. When you swap, we get this tree. 1 goes here and 7 comes here. So when we swap, we say that the last element. So we make the root of the max heap tree as the last element of the resulting tree. We say that now that last element is sorted. A4 is sorted. Why? In ascending order, last element should be the highest. That's what we call as ascending order. In ascending order, last element is the highest. So this is the last element. So this is now sorted. So next what? We should heapify A I0. A I is 4. A 4 0. Heapify A 4 0. A 4 0 is what? A 4 0 means a tree with size 4. Tree with size 4 means then this element is not there in that tree. This is removed. This is not considered. When we call this heapify A40, this this tree is of size 5. This tree, the heapifying tree is of size 4. So this is the last element is not considered. So why we call this heapify A40 is because is consider this tree with black elements. So this is no longer a max heap. This tree is no longer max heap because we exchange. We previously this was a max heap tree. Now this is not longer a max heap tree. We need to convert this one into again a max heap tree before we come back and swap again. Before we come back and swap again, we need to convert this into a max heap. So we call heapify for the root node of this resultant tree. Resultant tree is this last element removed. Right? So what will happen? We call the max heap, sorry, heapify for the root node. So now in the heapify function, so now you must have this understanding about this heapify function, which I already explained, using even an example. So what will happen in this heapify function? In the heapify function, inside this heapify function, so the first largest is set as this index, then it is compared with this one. Okay, this left element is greater, so now the largest element is 1. Then this will be compared with this element, this is less, so still the largest element is 6. So as the largest element is not equal to this one, we should swap 6 and 1, which will result this tree. And according to this heapify functions implementation, then it should call heapify for this one. Heapify A for 1 is called, but when one is called, it will make largest as 1. Then this 6 and 2 will be compared, but the fact is this one is already greater. This parent value, that means A1 is greater than its left child, so that this is already the highest, so that heapify will not, that means there will be no swap, that this will not be swapped, and the heapify will not take place again. So that means there is no change, right? So that means now this heapify A40 is over. Now we'll check whether this is a max heap tree. So we have to swap this one and come here. So 6 will go here, 1 will go here. Is this a max heap? We'll check. Sorry, so this swap A0 with A0 and A1 should be swapped here. So 1 will come here. So this one also should be swapped. So A0 and A1 will be coming here. Largest will be 1. So I have done it with a single step, so that I made the mistake here. So 1 will come here. After that, A4 1 will be called. Largest will be equal to 1. Then 1 will be compared against 2. 1 will be compared against 2. So now the largest will be 2. Largest will be 2. And so as largest is not equal to this one, this should be swapped. Swap not A0 but A1 with A3. Sorry, largest is here 1, and the largest will be 3 here. When 1 comes here, so I'll do it for this one. So this should be swapped. these two should be swapped. Right, so after doing this one, we'll go for here. So 1 and 3 should be swapped. Largest will be 1, then it will be 3, then a, the original index will be 1 will be swapped with a3, then the resultant tree will be this will be the max heap tree, and this 1 will come here and 2 will go here. Right, so this is the procedure of doing that. Then after swapping this one, then heapify a4 3 will be called, but it will not make any change. Heapify a4 3 will not make any change. And this is a max heap tree. Right, this is how this algorithm will continue to evolve. So now you must have understood. So we swap here, then we come to this point, then we call heapify a41, that means for this node, and it will check largest is equal to 1, and this will be make to 3, and this will be swapped, and again heapify will be called here, and no change. And this will be a max heap tree. So this is the first parent node, this is greater than this one, and this is the second parent node, this is greater than both of these two. And so then I will be decreased by again 1. So now I will be 3. Now I will be 3, and so this should be again change. This should be 1, this should be 2. And 6 and 1 will be changed. Here it will go 1, 2. 6 will be here, and here will be 1 and 2. And here will be 2, here will be 3, and here will be 1. Right. So I'll explain for one more iteration of this heap sort algorithm. So we obtain this max heap tree for I equal 4. Now I equal 3. So I equal 3, swap A0, A3. A0 and A3 is called. Swap A0 and A3 is called. Then it will result, these two will be swapped. 1 will come here, 6 will go here. And this is now already sorted. A3 is now already sorted. And then we call heapify. I is now 3, A3, 0. A3, the root node of the resulting tree. This is the resulting tree. 1, 2, 3. So heapify A3, 0 is called. So the largest is first set 0. Then it will be checked against this one. So now largest is made. Sorry, this is largest is made here 1. I change the value, so now the algorithm is also should change. Then this 2 will be compared against 3. 2 will be compared against 3. Then largest will be 2. Largest will be 2. So largest is first made 1 because 2 is greater than 1. Then largest is made 2 because 3 is greater than 1. Then we swap. So largest is 2. We swap A0 with A2 to get this tree. And we call heapify for this node, but A4 2, sorry, this should be A3 2, this is a leaf node, there is no change, so this is a max heap tree. This is a max heap tree, right? So this is how this heap sort algorithm works. I hope you got a clear understanding. So now by this time we have already sorted 2 elements. We can go on like this by repeating and sort all the elements of the array. So this is how heap sort algorithm is functioning. Right, so the time is up for today's lecture. So we'll conclude this meeting now, and you can